Next, we're going to look at the solutions to example sheet 8, which was delivered during the lecture on electromagnetic waves. So if we look at question 1, here we're asked to calculate the frequency of red light, which has a wavelength of 660 nanometers. So as always, if we want to find the frequency of a wave, if we know the wavelength and we know the speed of the wave, then we are using the equation C equals F lambda. So in this case, F is equal to C divided by lambda. So we just put the values into this equation. So this is the electromagnetic wave. So we know that C is going to be equal to 3 times by 10 to the power of 8 meters per second. And the wavelength of the light is given as 660 nanometers. So just be careful, that's 660 times 10 to the minus 9 meters. Nano is times 10 to the minus 9. So if we put those values into this equation, once again we've got a very large number divided by an extremely small number, so we're going to get a really large number, and this is going to give us a value of 4.55 times 10 to the power of 14 hertz. Or we can use, if we use the unit of terahertz, which is times 10 to the 12, which light is often expressed in, that's 455 times by 10 to the 12 hertz. Okay, so that's how we answer question 1. Okay, so let's move on to question 2. So here we're talking about an X-ray photon. So this is a kind of a photon is a way of looking at light as a particle with a certain energy, and here we're asked to calculate the energy of that photon. So the equation we're going to use here is this is kind of a small bit of quantum physics, where the energy of a single photon is equal to h times by f. So basically, if we know the frequency of the wave, we can work out the corresponding energy with a particle associated with that wave. So in this equation we have this one constant here, h, which is Planck's constant, and this is an exceptionally small number, because you imagine a single photon of light actually has a very, very small amount of energy. So in this case, this constant, Planck's constant, is actually 6.63 times by 10 to the minus 34 joules per second. But we're multiplying that by our frequency, which is 10 to the power of 18 hertz. So I'm going to multiply that by 10 to the power of 18, which is the frequency of the photon which was given in the question here. And so if we multiply these two together, then we're going to get a value, a very, very small value, which is going to be 6.63 times by 10 to the minus 16 joules. Okay, because we've got the 10 to the 18 here, then the 6.63 remains the same, and we're effectively just adding the indices here, so we get 10 to the minus 16. Okay, the second part of the question is saying that during a radiography scan, 10 to the power of 12 X-ray photons are absorbed by a material in 1 millisecond. So this material is basically the X-ray film. So what happens when you look at your X-ray scanner is you have a film here. Imagine put your hand in the scanner, and you can think of the irradiation by the X-rays as lots of these individual photons flying through your hand and then hitting the scanner at a point here. Okay, so basically it's saying that 10 to the 12 of these particles hit this film, this scanner here, in 1 millisecond. Okay, so that's 10 to the 12 in 1 millisecond. So it's asking us to calculate the power of the absorption. Well, the power is going to be equal to the total amount of energy absorbed in a given time. Okay, so in this case we've got each of these photons has this amount of energy associated with it. So in 1 millisecond, 10 to the power of 12 of these photons are going to hit this film. So the total energy is going to be equal to the energy per photon times by the number of photons. So it's going to be 6.63 times by 10 to the minus 16 joules but multiplied by 10 to the 12, because that's how many photons are going to hit in this time here. Okay, so that's going to be the total energy in that 1 millisecond. But then of course we've got to write that time on the bottom. So the time here is 1 millisecond. That's 1,000th of a second. Milli, remember, is times 10 to the minus 3. So that's actually equivalent to 0.01 seconds. Okay, so that's our equation here. And if we calculate what that's going to be, it basically comes out at 0.663 watts. So even though there's a tiny amount of energy associated with each photon, because so many of them are travelling through and hitting the screen here, we actually get a reasonable amount of energy that's being absorbed by the film. Okay, so that's the solution to question 2. So now let's look at question 3. What is the wavelength of a wave used to transmit a Wi-Fi signal with a frequency of 2.4 gigahertz? Once again, we're dealing with electromagnetic waves. We know the speed is equal to f lambda, so here we're asked to calculate the wavelength, which is equal to c divided by f. Okay, it's an electromagnetic wave, so it's 3 times 10 to the 8 meters per second is the velocity, and the frequency here is given as 2.4 gigahertz, so it's 2.4 times by 10 to the 9 hertz. Okay, giga is times 10 to the power of 9. Okay, so if we calculate what that results, then we're going to get a value of 0.125 meters, which is the same as the answer that's given there, which is 12.5 centimeters. Okay. So question 4 is asking us to describe how microwave ovens are used to heat food. So this goes back to the lecture, where basically we looked at the fact that most foods contain some amount of water, and water basically consists of an oxygen atom with 2 hydrogen atoms, which is why it's H2O. There's 2 hydrogen atoms attached to each oxygen atom. But what tends to happen is the configuration of the molecule is that the 2 hydrogen atoms sit slightly to one side of the oxygen atom. Well, and what this effectively does is it creates what's called a polar molecule, and there's an electric charge. Because of the way the electrons are shared around it, there's an electric charge difference from one side of the molecule to the other. So basically what that means is that there's a certain sort of polarity to the molecule. So if we then put an electric field across that, so we're constantly changing the polarity of the electric field, we have a charged molecule here, then that molecule keeps trying to flip to match the applied electric field. Okay, and if the electric field is sustained with really high frequency, then these molecules have to flip backwards and forwards at a very high frequency, and what that does is that generates friction within the molecules or between the molecules, and that friction actually generates heat and a rise in temperature for the system. So that basically is what happens when we put food in a microwave oven. We're flipping these things backwards and forwards at a rate of 2.4 gigahertz, so that's 2.4 billion times a second. We're trying to force these molecules to flip from one direction to another. So you can imagine that rate of flipping of this polar molecule is going to cause quite significant heating, and that's basically how they work. It's heating the water molecules in the food by this oscillating electromagnetic field. Basically, and the reason it works so well at microwave frequencies rather than other frequencies is because there's a certain kind of resonance with the water molecules. If you try and flip it faster, it can't keep up, and if you try and flip it slower, you don't get the same kind of resonance of this oscillation. So the sweet spot is around microwave radiation, about 2.4 gigahertz, to get this heating effect. Okay, so if we look at question 5. Once again, if we look at the lecture notes, we get a clear explanation of what's happening here. But skywave radio transmission describes transmission. So if we have the Earth's surface here, and we have, this is the ionosphere. this is a region in the atmosphere where basically that's lots of positive and negative charged particles kind of zipping around here. So there's lots of charged particles zipping around at this level, and basically when a radio wave is emitted from somewhere on Earth up, and it comes across this this particular layer of the atmosphere, these charged particles actually reflect the radio wave back down towards the surface of the Earth. Okay, and the good thing is that basically by having this reflection off this particular region of the atmosphere, because this is quite a long distance. This can be anywhere between 85 kilometers to 600 kilometers, so it's quite high above the Earth. That means that you can reflect waves, bounce it off the ionosphere, which means it goes around the curvature of the Earth, so you get much longer transmission of radio waves than you do by just direct line of sight, because the curvature of the Earth will interfere with that. Okay, and that's basically how it works. You can get these really long transmission distances because you can reflect it once or multiple times off the ionosphere, which allows it to effectively travel around the world. So it is this property of these kind of charged particles in the ionosphere that allow it to do this, but we do have to be a bit careful because the reflection is most effective for waves that have a frequency which is lower than 30 megahertz. Okay, so basically higher frequency waves, we don't get that same reflection behavior. We're dealing with much lower frequencies to get these long travels and long distance communication. But the particular property of the ionosphere is these charged particles that cause that reflection to happen. Okay, so let's look at question 6. So here we have a laser speed gun which is emitting a beam with a wavelength of 905 nanometers. Girls, shut up, I'm recording. So if we look at question 6, here we've got an infrared speed gun that's emitting a beam with a wavelength of 905 nanometers. So first of all, it's asking me to calculate the frequency of the beam. Okay, so the frequency is equal to c divided by lambda, which in this case is 3 times by 10 to the 8 because it's an electromagnetic wave which travels at the speed of light, divided by lambda, which is 905 nanometers, so that's 905 times by 10 to the minus 9 meters. And if I calculate the result of that, I'm going to get a value of 331 terahertz. Okay, it's actually 3.31417 times by 10 to the 14 hertz, so it's 331 terahertz. Okay, so that's my frequency. So carrying on, if the frequency shifts by minus 0.1 gigahertz when acquiring a signal from a racing car, what will be the beat frequency if the original signal is combined with the reflected one? Okay, so this is negative, so that tells me that the frequency is decreasing, so the racing car must actually be driving away from the detector, so something like that. And so this frequency is actually quite small compared to the frequency of the radiation as well. So if we're talking about beat frequencies, the beat frequency from the notes is just equal to the magnitude of one frequency minus the other one, basically. So here we've seen that that this is the frequency of the F1. So we need to know what F2 is. So F2 is just the frequency after this shift has happened, basically. So if I say that is F1, F2 is equal to F1 minus 0.1 gigahertz because it's going negative here. So basically it's a f1 minus 0.1 gigahertz, which is basically it's this value here minus 0.1 times 10 to the minus 9. Okay, so effectively this is quite a small number compared to this, which is quite a big number. So basically it's 3.314917 times by 10 to the 14 minus this is, if it's 0.1 gigahertz, it's 1 times by 10 to the power of 8 hertz. Okay, so basically I'm kind of 6 decimal places down here, so I'm going to get a value here which is equal to 3.31416 times by 10 to the power of 14. So it's a tiny amount that this frequency has actually changed. But then remember that the beats frequency is just equal to f1 minus f2, so it's the magnitude of this. So if I put these values in, I've just got so that f beats is just equal to 3.31417 times by 10 to the power of 14 minus 3.31496 times by 10 to the power of 14. Okay, and that's going to leave me just with a value that is 1 times by 10 to the power of 8 hertz, which is equal to 0.1 gigahertz. Okay, and that's basically because the beats frequency is just equal to the kind of shift. It's basically the same as the Doppler shift that's been recorded from this car racing away from the camera. So we'd actually expect this to be the case, that basically this shift is going to be equal to the difference between the two frequencies, which is why even when we work it through like this, we get a value that is directly equivalent to the shift that's given in the question. But just as it's a magnitude, it doesn't have the negative value in there. The beats frequency is going to be positive no matter which is the highest number. Okay, so that's the end of example sheet 8. As ever, if you have any questions, then send me an email or drop me a WhatsApp. Okay, thank you.